We are going to talk first about carbonic acid in water and all the benefits that we have seen for nutrient uptake from the plant. And also the second part of the webinar is going to be our friends from G.A.P that are going to talk about SAP analysis. First, I want to talk a little bit about myself. I've been involved in ag my whole life, since working in the fertilizer market since I was 17 years old. And then in 1994, I started in irrigation design, installation, system, drip, micro, all that kind of things. In 2003, I start doing all related with fertigation. So all those skids that you see around every farm right now, I installed the first one in 22 years ago, fully automated with managing fertilizer injection. On those days, we started thinking that the best way was electrical conductivity. We realized very, very quickly that it wasn't the right thing for farms. It was more for hydroponics. And so we switched to a proportional injection. And also I started doing water pH adjustment. And in 2013, I realized that we have to switch to something different and start researching about the carbon dioxide and the benefits and how simple it is to do it with carbonic acid. So since 2013, we start doing carbonic acid treatment. We came to California. Actually, I'm from Chile. I came to California and start showing farmers that there is a way, safer way. In those days, we were thinking that we were only pitching about safety and not all the benefits we have started seeing after the treatment with the carbonic acid. So 2016, we installed the first pilot, and today, 2025, we have more than 120 units installed and treating more than 13,000 acres of ranches with carbonic acid. So what we look usually is we all try to find or have the most sustainable irrigation water for our crops, right? So we get a lot of information on those analyses, carbonates, bicarbonates, RSC, electrical conductivity, SAR, nutrients, all those. Today, we're going to focus only on pH. Okay, most of the water samples that I have seen, either coming from district water, canals, blended water, is high pH, high bicarbonates. In the Central Valley itself is not that high in bicarbonates like it is in the Central Coast. The Central Coast is way higher on the bicarbonates, like probably sometimes double the bicarbonate we have seen here. So it make it harder to reach like an ideal pH. So when we have high pH in the water, we find that we have some difficulties on the farm in the production. And I'm going to start for the less important for us, and then focus a little bit on the most important one. For example, the less important or is important, but it's not the purpose of this webinar, is clog emitters. We have a lot of plug emitters, clog by scale. Sometimes if we have some organic, we have a blend of organics and scale. So we have an uneven distribution of water. That creates some different growth along the field. It requires more energy because we have plug emitters, we have emitters that are delivering more water. So it's a financial problem, and it's a water distribution problem. We also, high pH in water create another problem, that is less water penetration. Yeah, so we need to increase water penetration. And for that, we need to have a better water, a right pH in the water. And there's another one, is less nutrient availability. So we start seeing deficiencies on the trees based on this nutrient imbalance. Because even if we put the fertilizers, the solution in the soil is not the right pH. So the plant is hard for them to take it. So for that, I'm going to try to explain a little bit about this. There's a mineral imbalance. When we have, excuse me, when we have high pH in the water, As you can see, for example, phosphorus, magnesium is kind of okay, but all the micros are not available for the plant. Why is this? Because they are in a different form. There, for example, phosphorus can get some calcium phosphates, and we need to move it to make like a phosphate ion that the plant can take it. So we move the pH just to the right one, between 6.5 to 7, and we're going to have way more available phosphorus. The same with the micros. Calcium also is important. Calcium usually is in a carbonate form, and when you add, in this case, carbonic acid to reduce the pH, you make a calcium bicarbonate that is way more available for the plant. And if you have excess of calcium in the soil, so the idea here is we know we have a problem. We have high pH water, and we need to move it to ideal pH between 6.5 or 7. Okay, and there's different options. You have also a most popular one is the use of sulfuric acid or sulfur burners, and those clearly are not the best option, because at the end of the day, they create more problems in the long term than what nature is doing. So we have first the nutrient availability, and also we have the Justin von Liebig barrel. So, and these German scientist states that the best yield or the best potential of a crop is driven by the minimum factor. In this case, for example, in this slide, I emphasize the pH, but it can be sunlight, it can be chill hours, it can be different options. So it doesn't matter if you have all the rest of the duals of the planks of the barrel up to the top, you are going to be able to fill the barrel with water and to the top of the lowest or the limiting factor that you have. In this case, pH, or if the pH is not the right one, less calcium, or you don't have iron. So if you don't have different all to the top, the potential of your crop is not going to be the right one, or you're not going to get the maximum potential from the crop. So what is carbonic acid? Carbonic acid, here is important to understand that carbonic acid, the only way that carbonic acid in nature is added to the soil is through rainwater. There is rain, there is carbon dioxide in the atmosphere, and carbon dioxide is dissolved by the rain, get to the soil as carbonic acid. Okay? There are other sources of carbon dioxide in the soil, like respiration. Plant roots and soil microorganisms respirate, so they create carbon dioxide near the root zone. Organic matter decomposition, so all the microbes start breathing and releasing carbon dioxide. And the other way is to introduce it through the irrigation water. Okay, using the carbonic acid through the irrigation water create a lot of benefits for the plant. Carbonic acid slowly dissolve all the minerals that are in the soil. Okay, unlock all the cations that are tied to the clay or even to the organic matter in the soil, and release those nitrogen. Phosphorus, for example, as I said before. Then we have micronutrients like iron, manganese, zinc, copper, that become more available when the pH goes down than when you have a high pH. Okay. Also, calcium, magnesium, they are usually present as a carbonate form. If you add carbonic acid, you make a bicarbonate that is way more soluble and more available for the plant. And also, carbonic acid is a buffer solution for the soil. So preventing this drastic or dramatic increase on pH in the soil, keeping and maintaining the range of the soil pH in a more favorable for nutrient availability. Okay, and then as you can see in this slide, carbonic acid range from 4.6 to 5.5 in nature. In nature is around 4.4 to 5.5, but if you force the dissolution of more carbon dioxide in water, you can reach pH of 4.6 to 5.2 in pressurized system, fully dissolving carbon dioxide. Okay, and the other thing that is important is with the acid that are in the market right now, you have sulfuric acid, you have sulfur burners with sulfurous acid. There are some industries that use some kind of citric acid. That also something that you can use. But carbonic acid is a carbon-based acid. Because being a carbon-based acid, it's suitable for organic operations. It's more natural. As I said before, carbonic acid is exactly what nature is doing with rainwater. Okay. Another alternative or options on why carbonic acid seems to be more according to nature is that the root itself, they release carbon dioxide to the rhizosphere. So, and that blends and dissolves with the water that is near the root zone, making carbonic acid near the root zone. And that carbonic acid later, it exchange hydrogen protons for other cations that are in the soil, as I said, like copper, potassium, calcium. So this is something absolutely what nature is doing. Is part of all the ways that plants can take nutrients. This is one of them. And instead of the plant doing by itself all the time, releasing carbon dioxide, to make carbonic acid near the root zone, what we are doing when we add carbonic acid to the water, we increase that potential of exchange between the soil and the clay particles. Okay, they they dissolve and take all those tied up cation from the soil, and the plant make it in a more soluble form, and the plant can take it. I don't know. I think it's something that we have seen already, even during some soil samples that I'm going to show later. We have seen that there's more nutrients available after the use of carbonic acid than it were before, even if the farmer didn't apply any fertilizers on those with those elements or those nutrients. Okay. And to understand a little bit what is a carbonic acid is a form of carbonate in the water. So it's only related with pH. When you have high pH in the water, you have carbonates. And in the middle range between around 8, you have 100% of the carbonates in the water are present as bicarbonates. And when you start lowering the pH down, you start seeing that you have more carbonic acid. And when you have pH around 6.5, half of the bicarbonates that were present in the water became carbonic acid. Okay, and because when you add carbonic acid, you increase the volume or the proportion of the carbonic acid in the water, the pH goes down, and it still have all the benefits of having an acid in the water with the right pH and knocking half of the bicarbonates that you have present in the water at that time. We have seen also a lot of benefits when you use carbonic acid on spray applications. That means you have the carbonic acid, the water treated with carbonic acid, and you use that water to fill the sprayers, and then you save some of the money on the buffers that you're doing for the sprays. And we have seen a lot of increase on plant metabolism. It's, as I said, the slide says, is strength cells, promote the dissolution of organic and inorganic compounds in water, contributes to the ionization of the nutrients. And the ionization is make those nutrients that are in the water in a more available form. So whatever you're applying, foliar fertilizers, or you are applying pesticide, they make them more available or more rapidly available for the plant. Improve photosynthesis, improve all the nutrient absorption for the plant, because you are applying a water that is rich in carbon dioxide. And the plant recognize that, and the stomatas open, and they like it. And we have seen a lot of difference when you use like a water treated with buffers or when you would treat the water with the carbonic acid. To follow this, and we start doing since 21, we start taking soil samples and doing a B crop test with the lab named Biomakers. And because before that, the only thing that we were trying to do was replaces the harsh acids like sulfuric. So we start seeing all these benefits in the soil, but we didn't have any numbers. So we start doing these tests and comparing samples taken between March and August on the same range, on the same space. And this is part of the results that we have seen. I'm going to share with you guys. For example, this is microbial changes. This is not element itself, it's how the microbes in the soil are helping on different pathways. In this case, carbon fixation. And for example, on pistachios, all the samples are between 22 and 23. March 22, August 23, 3 years. We have seen that the microbes in the soil that process the inorganic carbon to make it organic compounds grow 40% in pistachios and 28% on almonds. The inorganic nitrogen release. We know that the plant take the nitrogen in an inorganic form. So they transform the organic nitrogen in inorganic so the plant can take it. On pistachios, 35%, on almonds, 34%. This is not the element again, I said, it's the microbes that help on this mineralization, for example, on the nitrogen. The same with the phosphorus, making inorganic phosphorus, solubilizing, and make it in a form that the plant can take it. 38 and 36, okay? Potassium, another one, 37 and 36. You can see that both crops is very similar, one with the other. So you have pistachio 37, almond 36. And now we switch from the microbial changes to a Haney test. Haney test is just physical chemicals changes. That means this is the actual nutrient. For example, in this case, total organic carbon in parts per million, they in pistachios grow 44% and in almonds 25%. The organic matter measured as loss of ignition change 6% in around 6% in my face is in the percentage and 16% in the almonds. Sorry. Electrical conductivity, that is a representation how much soluble salts you have when you have, especially this is California, so we're trying to reduce the electrical conductivity a little bit on the excess of salt in the soil. In both cases, the electrical conductivity went down, like up to 74% less in almonds. And here is something very interesting to understand here. So these two circles represent, the green one represents the first sample, and the second one represents the second sample. So, for example, on the pistachios, you can see that the total microorganism on the pistachios in the first sample, that means March 22, there were this universe of samples. And in August 23, the universe of microorganism is way more. For example, the total organism, what I did, okay, the total organism in March were 392 in general with all the samples. But in August 23 is 609. So it's more than 200 more microorganisms. But if you see here, there is an intersection between those two circles. All these, the intersection is the same type of microorganism, on the same microorganism. But the ones that are green out of the circle, they are not anymore present in the second sample. That means they switch or they die, they don't exist anymore. And all these new microorganisms grow. So it's not just only 200 units, 200 count that change. It's a complete different universe of microorganisms that grow after 2 years. The same happened with the almond. The almonds is less notorious because we have this some and probably this is the other one. So you can see that the difference between one and the other are the ones that they were not necessary. I don't have an answer for that. They were not necessary in that ecosystem that they change and switch to another type of microorganism. I have seen, for example, in growers that has nematodes problem, we have seen the microorganism that fights nematodes they grew 23% in 2 years. That means they're trying to help the farmer. They're not going to eliminate the nematodes, but at least they're making the environment less friendly, something like that. And here we have, for example, in pistachios, this is two different samples, 21 and 23. In the first sample, we have 392 organisms, and the one in September 23, we have 609. But you can see the different colors is what types of microorganisms are. The yellow are bacteria, the greens are fungus, and yeast. They show up a lot of yeast microorganism on 23 compared with the first sample. If you look at the size of the circles on the first sample, they were way more. And now you don't have those. You have completely different size, and you have way more small circles, and they're different. That's what I represented. The same happened with the almonds. Instead of 673, and it's more than 1,000 now. Different microorganisms. All of these are more than beneficial microorganisms. And just to finish a little bit, the presentation is like everything that I have said is why carbonic acid is a sustainable water pH control method. So we have a lot of different options. So it's biosustainable. So it's exactly what nature is doing. No increase plant resistant. We have seen more resiliences in the soil and increase the microbial diversity that is going to help the plant to fight with different needs that it has. NPK cycle, not only NPK, also micros. So the microbiology in the soil help to make all these nutrients more available. And when you do it exactly what we're trying to do with nature, we all like rain during the winter, and we have this salt leaching and get a more healthy soil. This is the same. In every irrigation, when you apply carbonic acid in the water, you're doing exactly the same as that nature is doing. Improve carbon sequestration, because we have seen that it improves total organic carbon, and that carbon is coming not only for the carbon dioxide that it was applied, it's also more this microbial activity that start accumulating more carbon. We have seen that even if you apply 300 or 400 pounds per year of carbon dioxide in the water per acre, you have 4,500 pounds of organic matter. So where is the difference came from? Not only for the carbon dioxide, it came from all these microbial activity improvement. Okay, it's safe. Carbonic acid is the same as rainwater, it's the same as club soda. So it's carbon dioxide in water, so it's no chemically it's completely safe. It's not going to happen anything to the user or the people at the ranch. Carbonic acid also proved to aggregate the soil, increasing water penetration, because take all that high calcium that it was keeping the soil together and aggregate it, improving water penetration, improving a glycoprotein that is present in the soil named glomalin, and that's sorry, that's one of the other benefits. That is the most the fastest one. This is one that you can see, like after 2 months of using carbonic acid in the water, you start seeing more water penetration and less water standing after the irrigation cycle. And my last recommendation for everybody is don't forget to check the pH. The pH is important. Give it the importance that it needs. Check the pH of the drippers. Check the pH frequently. The water pH during the season changes. Any method that deal with pH that is not acting as reading the pH in the water to solve the problem is not really effective. When you have any acid pump that you calibrate at the beginning of the season, is going to be completely different setup at the end of the season or during the season. So that's what I have to say now. Thank you, and I'm open to questions.
Thank you, Waldo. We've got a question about arbuscular mycorrhizal fungi, and she's curious why she didn't see any in the test. I believe that's because that's not in the B crop test, but maybe you can talk about AMF and how we kind of know that carbonic acid affects that.
The B crop test, it does measure what type of mycorrhizas we have, or fungi and bacteria, and even give you the ratio of the fungi bacteria ratio. And we have seen, just to highlight that part, we have seen that at the beginning of the season, usually we have like a 1 to 300 to 400 up to 1,000 ratio between fungi and bacteria. And at the end of the season, that goes close to 1 to 100, close to 1 to 200. So it does increase the fungi in the soil. And if you saw in the previous slides here, you can see that it's way more fungi here than it was in the previous sample. If it is a mycorrhiza or is a arbuscular fungi, it depends on the treatment or the soil itself. We have seen complete different changes in between the samples. We have been taking samples for 4 years now. This is the 5th year. I don't know if that answered the question.
I think we can email you also the data on the changes between the fungi bacteria ratio. But I guess the question is if there's specific species of the fungi in the B crop test.
They identify. Actually, I cannot do it now, but I can show you later. You enter. They have an app, like a platform, and you go there and you identify each of these circles that you see. If I touch it, it's going to tell me what species is, and in the results, you can go. It's very interactive, the platform. I tried to put it in a presentation, but it's extremely long to identify in a 20-minute presentation. But yeah, and I think that's it. If you reach out to the people from B crop, it's going to be very interesting because they have a lot of experience in complete different all over the world, not only California. That is the experience we have. This is the result of samples that we voluntarily take on the ranches that we have been treating with carbonic acid for many years now.
If I can ask something, Waldo, what is that difference? A lot of times people talk about wanting to control their soil pH, but you're talking about controlling the water pH. And soil pH is sometimes influenced by water, sometimes influenced by other things put into the water, even by nutrition applied in the water. So why should people not worry about their soil pH? Should they just worry about water pH? Should they worry about both? Like some people put acid into the soil to change the soil pH. Like how do all those things fit together with carbonic acid that comes in through the water?
Being more than, I don't know, 21 years dealing with with pH itself since 2003, I have seen a lot of different approaches to deal with pH in the soil. And most of the time, farmers rely on very strong application of acid. Even I have seen people spraying acid in the soil just to change the pH in the soil. But at the same time, they apply this acid, sulfuric acid specifically, and then they irrigate the whole season, 2, 3, 4 acre-feet of water with a pH of 8.5 and 300 parts per million of bicarbonates. So whatever they did before, they don't even offset what they were doing. If you always irrigate with the right pH in the water, you're going to have the solution near the rhizosphere on the right pH, and it's going to make all these more easy for the plant to take the nutrients. And when you choose the right acid, in this case, carbonic acid, that is way more natural than any others, you're going to see a complete total response and different response from the plant. The soil is important, the pH is important in the soil, but it's way more important to treat the water because it's the more immediate reaction between the plant and the soil and the solution. That's why it's so popular now, the fertigation. So you apply fertilizer proportionally dosed what the plant needed and the season they needed, and also you apply with the right pH. You make all these investment that you're doing way more available, and you don't waste excess of fertilizers. You have readily available for the plant on the solution.